Let's look at an example with some electrical components. So let's suppose we have a capacitor that is 5 microfarads, so that is 5 times 10 to the negative 6th farads, which is kind of a typical value for a capacitor. Let's find the value of an inductor that would cause the circuit to oscillate at 1,000 hertz, so 1,000 cycles per second. And when we set this system up, if we suppose we charge it with a 20 milliamp current and no initial charge on the capacitor, let's write the capacitor charge as a function of time. So for part A, we know the frequency we want. The frequency is 1,000. And that means that the period is 1 over 1,000. So 1 millisecond, I guess. And remember, omega is 2 pi over the period. Or another way to write that is, right, since the period is 1 over the frequency, omega is 2 pi times the frequency. So that's going to be 2,000 pi. Okay, so we need omega to be 2,000 pi. But remember, when you're working with a capacitor and inductor, oops, I'm missing a 0 here. When you're working with a capacitor and inductor, omega is the square root of 1 over LC. Okay, so we can maybe rearrange this to find LC. So square both sides and take a reciprocal. We get 1 over 2,000 pi squared is equal to L times C, but we know what C is. Our capacitor is 5 times 10 to the negative 6th farads. And so we just need to solve this for L. So let's see. 1 divided by 2,000 times pi squared. So that left-hand side is 2.5 times 10 to the negative 8th. So we're going to divide that by 5 times 10 to the negative 6th. And we get that L should be 0.0051 approximately. And this is in henries. So this is about 5.1 millihenry. Okay, so now that we know the component value for L, we can model this situation using our usual differential equation. So for that differential equation, right, we should write all of our units in farads and henries just so that they're compatible, right? If you mix microfarads with millihenry, your units aren't matching. So, so remember, we're going to write down L times Q double prime plus 1 over C times Q equals 0. So L is 0.0051 times Q double prime plus, so 1 over C is going to be 1 over 5 times 10 to the 6th. So that times Q equals 0. Now we know what omega we should get, right? We should get omega should be 2,000 pi. So we can jump directly to writing down our solutions. So it's going to be some constant times sine of 2,000 pi times t plus some other constant times cosine of 2,000 pi times t. Okay, now we just need to use our initial conditions to find these constants. And remember, our initial condition was that initially there's no charge and the current was, what was it? 20 milliamps. So that's 0.02 amps. Okay. So 0 is y of 0, but y of 0, if we plug 0 into here for t, the sine part goes away, the cosine part turns into 1, and we just get c2. So now we know c2. The derivative of y, right, the cosine part is gone now because c2 is 0, so we just need to take the derivative of the sine part, and we get 2000 pi times c1 times sine of 2000 pi times t. And so now use the initial condition. Y prime of 0 is supposed to be 0.02. And when we plug in y equals 0, or plug in t equals 0, we get into y prime, we get 2000 pi times c1. And so we can do the arithmetic to find c1. It's going to be some nasty value, 0.02 divided by 2000 divided by pi, 0.0000318. So that's what, 3.18 times 10 to the 1, 2, 3, 4, 5, negative 6. Okay, and so now we have our the behavior of the charge on the capacitor as a function of time. It's 3.18 times 10 to the negative 6th times sine of 2000 pi t. And there we go.